Hi, folks. There is a very good article on the with the title Names, Scopes, and Bindings. This is with reference to programming languages. And I'd like to quickly go through it and explain things which could possibly be a bit confusing to newcomers. All right, so overview: names, binding time, object lifetime, object storage management, static allocation, stack allocation, heap allocation, scope rules, static and dynamic scoping, reference environments, and overloading. All right, so we move to the next place. Names and abstractions. What's in a name? Well, everything. So, what does this guy say? Names enable programmers to refer to variables, constants, operations, and types using identifier names rather than low level hardware components or addresses. So, name is a convenient handle. Uh, by the way, this is not just limited to programming languages or software design alone. The capability to name things is a critically important capability that we as humans have, and it is linked critically to the power of abstraction. It is only when you name something, whatever that might be, then you don't need to think of other details except its name when you use it in further top level building blocks. So we'll see that. So names also form control and data abstractions for complicated program fragments. Control are things like even function calls are control and looping constructs, labels, so on and so forth, and data structures. Yeah. Control abstractions, subroutines, procedures, and functions allow programmers to focus on a manageable subset of program text. Yes. Subroutine interface hides implementation details. Yeah. A subroutine or a function. As long as I have a function named sort, which I can give an array, my array, whatever array, as an parameter, as long as it really sorts it, I don't really care how it does that usually. At least that's the idea. So yeah, that's the power of naming and abstraction. Moreover, data abstraction in object oriented classes hide data representation details behind a set of operations. So yeah, it's in object oriented design and programming, you don't want the data members to be directly changeable. Instead, you access it through methods, right? So that again is abstraction. And it happens through names, names of the variables, names of the class, names of the functions, member functions, accessor functions, all names. Abstraction in the context of high level programming languages refers to the degree or level of language features. That's right. Or it's, in other words, that abstraction is also an indicator of the expressive power of a higher level programming language. That is, you can get more done by writing less, right? The rest, other named things do the rest of stuff for you. All right. So that gives you level of machine independence and the power of constructs. That is what we were talking about. So next we come to the concept of binding time. A binding is an association between a name and the thing that is named. All right. So my name is Taha. Whenever I was named by my parents, a binding was done that, hey, this newborn baby of ours, his name is Taha. That's it. So binding time is the time at which an implementation decision is made to create a binding. So all of this happens in a context. At some point you need to make that decision. Okay, from now on, this thing is called this, right? And that attachment is also time bound. It is not eternal. And that decision of when to create that binding, how long does that binding last and why, that is also part of the design. In some cases, the design of a programming language. And then the same holds true in when you're writing application programs. You create your own choices of using different aspects of the language. You need to be aware of the features. So we'll see that. So language design time. These are the different times. The design of a specific program constructs, syntax of the language, primitive types, and meaning. So that is, for example, in C, int is a keyword, right? So these are all keywords and the constructs associated with them and the meaning associated with them. The meaning is that the compiler will enforce, and the syntax it will also enforce, right? So let's see. Language implementation time. Fixation of implementation constants such as numeric precision, runtime memory sizes, maximum identifier name length, number and types of built-in exceptions, etc. Right? So yeah, language implementation time means that when a compiler is written for the language. Program writing time. So using that language and its compiler or interpreter, whatever, you the programmer is makes a choice of solving a problem by you using some algorithm, data structure, and code, right? So compile time, the time of translation of high level constructs to machine code, and the choice of memory layout for objects. So this is a time at which the compiler does a lot of these things. As long as you're abiding by the syntax of the language, you expect any compliant compiler to do the right thing, to compile it and give you an executable, right? But for compiler, that is a lot of work, and we'll see. Link time. So link time is the time at which multiple object codes, think of them, let's say, as different libraries, you know, which you can link together in and use in your application program. So the linker does these things. And libraries are combined into one executable. So clearly the names that are used in other libraries that you're using and vice versa become relevant. Load time, the time at which the operating system loads the executable in memory. So the particular component is, it's called the loader, basically the program loader. And that is what happens when you execute that program, right? The control goes to the operating system, it does something with it, and bingo, your program runs. And runtime, the time during which a program executes. So a program is running, um, and you could create new constructs during at some point in time while the program is running. So typical is dynamically allocated memory. That's how it typically is managed. So binding time examples. So we have, let's say, if a is greater than 0, then b is equal to a. By the way, this is not, this is pseudocode. This colon is equal to, it shows assignment, um, so on and so forth. So this is all of this is at language design time, right? When you're writing the specification of a language, you decide these things carefully. And then the internal representation of literals. For example, how is 3.1 this floating point constant? How is it represented in memory? How is it supposed to be represented in memory? You can't just leave that to chance or randomness, right? You, in order to work together with other libraries, and you have to be precise about it. So yeah, that is a time at which language implementation is done, which is to say when a compiler is written for whatever that language is. The specific type of a variable in C or Pascal, let's say, uh, compile time. For example, you uh, tell that in C, let's say, you tell that a variable is integer or float or character or whatever. So that these decisions happen in compile time. All right. So storage allocation method for a variable, language design, language implementation, and compile time. We'll see more as we go. So linking calls to static library routines, for example, printf in C, this function is printf and other similar functions are made available as part of the C runtime library, right? It's a library. It's a standard library. And the linker is aware of it. The linker that is part of the C development tools is aware of that through the path and all. So merging multiple object codes into one executable, yeah, we saw that's the job of a linker. And the loader loading executable memory and adjusting absolute addresses. We'll see. Non-static allocation of space for variable runtime. So these are all things like dynamic allocation of memory and stuff. All right, so the effect of binding time. Early binding times, that is before runtime, are associated with greater efficiency. Why is that? Because you already know a lot. If you can factor in some optimizations based on that knowledge, then you're clearly efficient, right? Compilers try to fix decisions that can be taken at compile time to avoid to generate code that makes a decision at runtime. Syntax and static semantics checking is performed only once at compile time and does not impose any runtime overheads. So C is a typical example of a language that tries to do as much as possible at compile time. So late binding times at runtime are associated with greater flexibility. So yeah, this greater flexibility is a double-edged sword, right? Will for example, JavaScript is an example of this, right? Where you have loosely typed variables, and you can assign one variable, whatever it happens to be, into the other, an integer into a list or stuff. Interpreters allow programs to be extended at runtimes. Yeah. Languages such as Smalltalk 80 with polymorphic types allow variable names to refer to objects of multiple types at runtime. So yeah, Smalltalk specifically is an entire what do we say? It's sort of it's not just it's an entire environment. Smalltalk method binding. So Smalltalk is not really used much, but so we'll move on. Method binding in object-oriented languages must be late to support dynamic binding. All right. So one reason of this is that you don't really know, depending on your class hierarchy, that in this specific moment, which specific method, let's say if multiple methods exist in the class hierarchy, let's say you're using an object of class X that is derived from class A, which is derived from class B, and the same method exists in all three of them, right? A lot of things matter there, depending on if you that's all polymorphism. It's pretty I think it should be clear that why there is a need of such a thing. All right, so object lifetime. Key events in object lifetime is object creation, creation of bindings, reference to variables, subroutines, types are made using bindings. So whenever you need to understand one thing, anything that is handled by a name, right? And that is pretty much a lot, pretty much everything. For that, a binding is needed. Whenever a binding is needed, a decision is needed when to create that binding, what are its implications, and when to end that binding. All right. So deactivation and reactivation of temporarily unusable bindings. Yeah. Destruction of bindings, destruction of objects, binding lifetime, the time between creation and destruction of binding to object. Yeah. So over here, there's a named object. For example, a Java reference variable is assigned the address of an object. Yeah. For example, a function's formal arguments is bound to an actual argument. Okay. Object lifetime, time between creation and destruction of an object. So yeah, it's nice. So let's see. So let's see. There is a C++ fragment. There is some class, and there's a reference to that class's object. It's called my object, and some class, a new instance has been created, and then it has been dereferred and assigned into my object, right? So after this, let's say, what is this guy doing? There is my object reference. And the same reference is now pointing to some other class. So my object over here is bound to other object, which is this whatever this instance was that was created over here. After this immediate line of code, this is what it points to, refers to. And after the end of this block, my object is now again back to this guy, right? Because its scope has changed. And then you delete my object, it was just a reference, it will get deleted. All right, so what is this guy saying? Object creation in memory and object destruction. And this is time, yeah, that's how it's up. Creation of binding to the object, binding of object temporarily invisible as it, if you see above, when you are in this internal block, this top binding was invisible because of the scoping rules of the language C++. And once this internal block is ended, then it's visible back again, right? This guy is visible back again till the time it is deleted explicitly, or gets out of scope and gets deleted. All right, so object storage management. An object has to be stored in memory, of course. Where else would it be stored? Static objects have an absolute storage address that is retained throughout the execution of the program. That is important to know. So they are global variables. They could be subroutine codes. There could be class method codes. And this happens in C and C++ often. Stack objects are allocated in last in, first out order. So this, as you might remember, stack is a data structure and last in, first out is how it behaves, LIFO. Usually in conjunction with subroutine calls and returns. Yeah. Actual arguments of a subroutine, local variables of a subroutine. So whenever a subroutine is called, what objects are pushed into the stack? The arguments that are passed on to that function, that subroutine, they are pushed. And also all the local variables of the subroutine, they are also pushed to the stack. And they are popped on their way back, right? And this is also how, we will see later. This is also how any called function knows where to return its control back once its execution is over, right? All right, so heap objects may be allocated and deallocated at arbitrary times, which is to say dynamically, but require an expensive storage management algorithm. So this is, for example, in C, this is what malloc does and its class of functions. Basically, it's dynamic allocation. And C++, it's what the new operator does. And in Java, I think new is the operator in Java as well. All right, so, but it has its associated, as this guy says, storage management algorithm. In C++ as well, and in languages like Java, there is garbage collection going on, so there's additional stuff that happens. All right, so typical program and data layout in memory. Program code is at the bottom of the memory region, right? So this is the executable code, the instructions. Static data objects are stored in the static region, the data section. These are the globals, so to say, which retain their um, presence throughout the program executable time, right? Stack grows downward, this goes downwards. This is used for function call arguments and its local variables. Heap grows upward, so the heap is used for dynamic memories. So this grows upward, and this is the entire memory layout. This memory layout too, by the way, is not um, it's not really the real memory addresses that we are talking about, because remember, the job of an operating system is to abstract that out from you. But that's a discussion for another time. All right, real or not, the address is there. All right, so static allocation. The program code is statically allocated in the most implementations of imperative languages. Statically allocated variables are history sensitive, which means they retain their history, because think of them as global variables. So static local variables in C function retain value even after the function returns. So if a function has a static local variable, if memory serves me right, then the function itself also needs to be declared static, right? Because it retains the value of its static variables. Advantage of statically allocated object is the fast access due to the absolute addressing, right? The address is just there. Once assigned, it's just there, right? When the subroutine is called again and again and again, there is no need to create new memory and push it into the stack for at least that variable. The same address is relevant. So yeah, it's fast. Static allocation does not work for local variables in potentially recursive subroutines. Every recursive subroutine must have separate instantiations of local variables. Yes. Otherwise, what's the um, recursion fails, right? But this calls for another discussion. For the time being, this is all right. So Fortran 77, just to give you an interesting thought, try doing something. Try having a recursive function call, define a recursive function, and do not set an exit condition that breaks out of the recursion and call that function. You'll have what is called a stack overflow, right? Because there is no space left in the stack to keep on pushing the functions being called in a recursive fashion, right? The stack size is limited after all, whatever that might be. All right, so Fortran 77 has no recursion. It does not support recursion. Both global and local variables can be statically allocated as decided by the compiler. Avoids overhead of creation and destruction of local objects for every subroutine call. Yeah, these are the design choices of the language. So what is this guy saying? Typical static subroutine data memory. Local variables, temporary variables, bookkeeping. This is what the compiler and the operating system they do stuff. And the return address where to return, return to the caller, right? This is the callee. You have to return to the caller and the arguments. All right. So we move forward and we go to the stack-based allocation. Each instance of a subroutine at runtime has a frame on the runtime stack. So yeah, frame is nothing else but mm, it's just an abstraction. You just push stuff in the stack basically, and you give it a name also. It's a frame, right? So whenever there is a chaining of function calls, function A calls function B calls function C calls function D. So each of those functions in the chain has its frame in the stack, which you can observe in a debugger. And what really is that frame? It's just a collection of uh, memory and its interpretation, basically. So compiler generates subroutine calling sequence to set up the frame, call the routine, and to destroy the frame afterwards. Subroutine prologue and epilogue code operate and maintain the frame. So the prologue is what happens earlier, the epilogue is what happens after. Frame layouts vary between languages and implementations. Yes, they do. Typical frame layout is that, there are arguments, return addresses, bookkeeping, local variables, and temporaries. All right. A frame pointer points to the frame of the currently active subroutine at runtime. So if you debug, for example, any code, typically in C or C++, you can easily, inside the debugger, um, if you take a stack trace, right? If you take a stack trace, it will give you the entire list of these frames, where each frame gives you the observation into everything that is available in that point and chain wherever you happen to be, and that is you're observing some function in the entire chain. All right. At runtime, Subroutine arguments, local variables, and return values are accessed by constant address offsets from the frame pointer. All right, so yeah, this is how the compiler actually does it, right? We don't know about it. For all that we care, it's just a syntax of the language. But for the compiler, whatever that frame, the current frame is, right? It has an address. That address is referred to as the frame pointer in the current context, and the different variables available inside that frame. So let's say you are in function A calls function B, function B calls function C calls function D. Let's say I'm inside the function C and I break into the debugger, right? So I will be observing the frame of function C, right? And I'll be able to observe the different variables, the arguments that are relevant at that frame. The debugger, through the use of symbols, additional debug information, gives me fancy names, whatever the names I chose in the programming language. But for the compiler, for the actual executable, the only thing that matters is the address of whatever that named entity is, whatever variable or whatever, right? All right, the stack pointer points to free space on the stack. So this is how the it's all managed, this entire thing. All right, so we have a stack based allocation example. So let's say this is a good example. It will become somewhat clear. All right, so this is a main program. That you have the main program, you call function A, and what happens in function A, B is called. What happens in function B, A is called again. All right, so this is somewhat indirect recursion. um, and if there is no exit condition, that it will keep on building till the time the stack is overflowed. There is no resource on the stack, but I'm assuming that there would be some exit condition. So let's say main calls A calls B, B again calls A. All right, we are inside the main program. So main calls A, right? And all its temporary variables, all its arguments are pushed. Return addresses are pushed. The return address of the main program is pushed, where at whatever point of the main program A happened to be called, just immediately after that, that would happen to be the return address. So whenever the control is given back to main, one needs to know where does that control go. So that is why the return address is pushed. There's some bookkeeping stuff, local variables and temporaries, as we saw. The same happens when the subroutine A calls subroutine B. All of these things are created for the subroutine B. And now the return address will be that of um, this point, just immediately after B is called. Because whenever this call to B is completed, what do we expect? We expect that the next line of code, whatever is corresponding to it, should start getting executed. All right, so now we are in B, and then again A is called, right? So subroutine A, same stuff happens again. Okay, so current frame at this point, let's say, at this point, the current frame pointer is pointing to this frame, right? Because this is the active frame. And the stack pointer is pointing to the next free space wherever it happens to be in the stack. So I think this really explains it, and we move forward. Word sizes of the types of local variables and arguments determines the frame point offset in a frame. So offset is the address offset. So frame pointer is where the start of the current frame, whatever that happens to be, is think of it as a base address, and you add to it some number, and it gives you the address of some variable, some area of memory, which has a meaning by virtue of just being there, having a name and meaning. But when we are talking about the details, the name does not matter much. It's the fact that whatever I'm dictating to the compiler through my source code, through my fancy source code. The compiler is honoring it. That's all I care about, right? All right, so this is Pascal. I don't know Pascal, so I'll just ignore this. Heap based allocation. So there is implicit heap allocation. For example, Java class instances are always placed on the heap. That is a language choice. Scripting languages and functional languages make extensive use of heap for storing objects, right? Some procedural languages allow array declarations with runtime dependent array size. If I'm not wrong, uh, even C now allows it for a while. Resizable character strings, explicit heap allocation statements and or functions for allocation and deallocation. These are things like allocation, alloc, scalloc, calloc, malloc, this class of functions in C, or new and delete in C++ and Java. All right. So heap allocation is performed by searching heap for available free space. This is, by the way, what the heap manager would do, whatever the heap manager you're using. We are not bothered. For all that we care, if we ask for a certain amount of memory, we expect that it will be given back to us, and all the heavy duty work of finding it the right place for it in the heap will be done by the actual heap manager. All right. So let's not bother about the details. Let's understand the concept. So at some point in time, you request allocation for object E of 10 words, right? Um, let's say deletion of objects leaves. There is fragmentation. This is, let's forget this for now. The idea is that heap management in itself is a complex thing, because you have to be able, for any heap manager, you have to make it efficient. For example, the availability of contiguous free space matters. For, let's say I have, let's say, 5 bytes free at some place, or 5 word space, as this guy says, and then 10 bytes are busy, used somewhere, and then I have 2 bytes, and then I have 20 bytes free. And this pattern, let's say, repeats for 20 minutes, no, 20 minutes, 20 times, let's say. So even though there's a lot of memory that is free, but if I need, let's say, 100 bytes in a single allocation, I don't have it. I don't have it contiguously, right? So this is just one of the problems that a heap manager has to effectively solve. And there are many heap management algorithms. There are third-party heap managers, so on and so forth. But this is basically the job of a heap manager. All right. So heap allocation algorithms, here this guy is touching somewhat um, on it. So typically you study this in a compiler design course, or and in an operating systems course. So heap allocation too is, despite its special function, it's just another algorithm, right? It's an algorithm. You would be needing some data structures for it. So internally, what happens is that typically it's implemented through linked lists. You have pointers to free spaces, so on and so forth. Um, so yeah, these are some algorithms, and you can of course see the details. There are many more algos too. All right. So next we go to garbage collection. So garbage collection, in a sense, is the process. Think of it this way: in C and in C++, memory management is a real pitfall. If you don't do it well, then you have memory leaks, which is to say you create memory for whatever you needed it for, and then you forgot to destroy it when it was no longer needed. If such a code path, if such an area of code is in a frequent code path, then you will keep on losing memory, which you could have used. So many garbage collected languages like Java, for example, solve this problem by keeping track of um, allocated, dynamically allocated memory And what they do is that they themselves destroy any memory which you forgot to destroy. All right. So how do they even know that I forgot to destroy? Typically, what they do is that they maintain a list of whoever is pointing to that memory. If the count of the names or variables pointing to that memory reaches zero, right? Then the garbage collector goes ahead and destroys it, even though you have not. So there are many. This is the essence of it, and you know. But then again, efficient writing, efficient garbage collection algos is not very easy, but it's done. It's now done in many languages. All right. So explicit manual de-allocation errors are among the most expensive and hard to detect problems. Yeah, in C and C++ typically. If an object is deallocated too soon, a reference to the program to the object becomes a dangling reference. That is, if you what a dangling reference means is that, and again, it's a typical programming error in C and C++, that you happen to destroy the memory, right? And after it has been destroyed, you try to access it using some name, right? So it becomes pointless. It would be pointing totally somewhere else, not where you think it would be, right? So this is called a dangling reference. All right. So if an object is never deallocated at all, then the program leaks memory. That is what we just discussed. And automatic garbage collection removes all the objects from the heap that are not accessible, right? So this is the essence. That are not accessible. That is, they are not referenced. That is, there is nothing that points to it anymore, right? Because if you, as the application programmer, needed that memory, the only way you would be able to access it through your code would be through some name, some named variable. If at any given point in time of program execution, no such named variable exists, then that means for the application programmer and program, whether that memory exists or not is immaterial, right? Since it's immaterial, the garbage collection goes ahead and destroys it. It's being wasted, right? That is the thing. All right, so it is used in Lisp, Scheme, Prolog, Ada, Java, and Haskell. I believe it's also used in .NET. Disadvantage is that there's an overhead, right? The garbage collection is a process. It needs to take care of things. There's an overhead, but the algorithm efficiency has been improved. Yeah, it's very common. Moreover, the hardware is getting faster, so that overhead is acceptable now, corresponding to the immense value that you get from it. All right, so not always suitable for real-time programming. Yeah, I think no, never suitable for real-time programming, truly real-time programming, when you need to have predictability more than anything else. Garbage collection is not your friend, right? Because garbage collector, by the way, can be invoked explicitly, usually in all languages that support it, but they also it also fires at a time of its own choosing, right? And that time of its own choosing, of course, is not free, right? It's not free. It uses computational resources, processor time, memory. So in areas where real-time constraints are important, you do not use garbage collection at all. What could those areas be where even nanoseconds, microseconds of difference is the difference between life and death? Think of aircraft traffic control, um, or the software that uh, controls a ventilator, for example, computerized ventilator, or the software that controls the nuclear missiles of any nation, right? Etc. So this is a quick comparison. All right, scope. All of this is related to scope, of course. The scope, the textual region of a program in which a name to object binding is active, right? That is what we said. Statically scoped languages, the scope of binding is determined at compile time. This is important. C is the most um, active and famous proponent of this approach. C would rather want you to have everything clearly specified at, and the compiler should have visibility over it so it can enforce the type checking, and it gives you many benefits that come from it. All right, so used by almost all but a few programming languages, more intuitive to use compared to dynamic scoping. Yes. All right, dynamically scoped language, the scope of bindings is determined at runtime. All right, so this is a double-edged sword, right? So there are many nasty bugs that can hit you this way as well. So, for example, it's used in Lisp, APL, Snowball, and Perl, and it is also used to various degrees in other languages that we are more familiar with today. For example, JavaScript. And anybody who has used these dynamic languages, you know, it's easy, certainly, very easy, but it's at a cost. You better use it carefully. Otherwise, crazy stuff can happen, things that you did not intend to happen, things that a statically compiled compiler is no longer there. A compiler for a statically typed language is no longer there to check for, like in C, right? So it adds some burden um, of knowing what you really are doing to the programmer, because if you're not careful as a programmer in a dynamically typed language, then you can expect many nasty bugs which will occur at runtime, and each time they will likely happen differently. So it's convenience, but we need to use it with caution. All right, so static versus dynamic scoping. The following pseudocode program demonstrates the effect of scoping on variable bindings. All right, so A is an integer procedure first. A is assigned the value 1. Second procedure A is an integer. It calls the first procedure, okay. And then we have the procedure main. A is equal to 2, calls the second, write integer A. All right. All right, so let's see. Binding with static scoping, program execution binds A in first to global variable A. All right, so it did not make it clear. This is a global variable. Okay. Okay, of course, that will be the binding. Okay, this is the global variable. First main is called. So A will be assigned the value 2. Then the second function will be called. And inside they have an A integer. Then first will be called. And when you are inside the first function, which is this guy, A is assigned 1 inside this first function. But the thing is, inside this first function, A is not defined, right? So even if there is a hierarchy of scoping, even if you could have a global variable with the same name and a local variable with the same name, and you could define order of priority of scope, over here it's irrelevant, because this A is equal to 1, the assignment will clearly be done with against the global variable. And that is exactly what happens here. This is exactly it does. So write integer A, and whatever that program does, it prints to console probably. So the value of A at this point is 1. All right, so let's say if the same thing were to be happening with dynamic scoping, so what would this do? Binds A in first to local variable A of second. All right. So C does not really have this rule. I don't know which language this guy is referring to, but let's say if there were a hypothetical language, you have a global variable A, which is an integer. You enter main, you assign 2 to it. Then you call a function called second. And inside that function, there's a local variable A, which is an integer. So there is some sense of priority that inside the scope of the second function, this has precedence when instead of the global variable, right? and then you call first. And inside first, A is assigned 1. Then you write integer A in the outer scope. So over here, as per this guy, the program will output 2, which is the last value that was written to the global variable. Because at this point in time, the stack frames of this function second and first are just no longer there, right? They were local non-static variables, and that is what has happened. There is an assumption here, by the way, which is that the assumption is that the local variable a, which is present, which is a local variable of available inside the frame of the function second, is also available inside the function first. So this assumption is not valid in C, but it must be valid in some other languages. All right. But whatever this guy is telling us, that we know. All right. So let's move forward. The bindings between names and objects can be determined at compile time by the examination of the program text, which is the source code. Scope rules of a programming language define the scope of variables and subroutines, which is the region of program text in which name to object binding is usable. So yeah, that is what a language tells you. The rules of the scope, as part of learning a language, you have to know them. The job of implementing that as per the contract defined by the language is that of the compiler. But you as an application programmer need to know, be aware of it so that you can use it deliberately and not get bit by the bugs that an incorrect understanding would lead you to. All right. So early basic, all variables are global and visible elsewhere. Yeah, Fortran 77. The scope of a local variable is limited to subroutine. Scope of global is the whole program text unless it is hidden by a local variable. So hidden, what does that mean? That a local variable with the same name exists. Declaration with the same variable name. And Algol, 60, Pascal, Ada, these languages now allow nested subroutine definitions and adopt the closest nested scope rule. So this was actually the rule that I was mentioning. See, let's go back to this guy, this example, right? So what I was mentioning here there is that inside the first, the stack frame of the first, when we assign the value 1 to a, why did it not assign it to the global variable a? Instead, how did it even know that it has to assign this value to the local variable a, which exists in its caller, which is second, right? So C does not behave this way, but this guy illustrates it that some languages have what is called as the closest nested scope rule. That is exactly what it would do in such a language, right? Okay, let's move forward. Closest nested scope rule. So I think we don't need to look into this. You can study it yourself. I have already gone through how this is interpreted. All right. So implementation of scope. Let's see this. Scope rules are designed so that we can only refer to variables that are alive. Yes. And also because of their utility, right? You know, we design rules so that they serve some purpose to the application programmer. The variable must have been stored in the frame of a subroutine. Exactly. If it is not stored, then how do you use it? If the variable is not in the local scope, we are sure there is a frame for the surrounding scope somewhere below on the stack. What would that be? Somewhere below, it would be some of some of its caller, right? So think again. Function A calls B, B calls C. So inside C, you access a variable, let's say named X, but it's not there. It's not defined in C. So what would it do? It would check if it's a local variable exists. If there isn't a local variable, then it would see what is the closest next frame. It's B. If it finds in B, then it would uh, click to the, it would class to that and use it. If it's not in B, it would go to A. If it finds there, then it would use that. If it's not even there, then it should be an error, right? All right. So this is how this is implemented, and we can see this, right? It's easy to go through this. All right. So bindings to non-local objects, static chains. The static links form a linked list of static parent frames. All right. When a subroutine at a nesting level J has a reference to a local object of a surrounding scope nested at level K, right? At level K minus J, static links form a static chain, right? So all of those framed in that chain are accessible, are accessible to the subroutine at nesting level J. They are very much accessible. Is traversed to get to the frame containing the object, and depending on the rules, you can traverse that chain till you find the the named object, the variable that you were looking for, whether to read it, whether to assign something to it, right? So, for example, a subroutine A is at nesting level 1 and C is at nesting level 3. When C accesses a local object of A, two static links are traversed. Yeah. All right. Non-local objects can be hidden by a local name to object bindings, and scope is said to have a hole in which the non-local binding is temporarily inactive but not destroyed. So this is basically what this guy is saying is the same thing which we talked about. Let me see somewhere over here. See, so binding to over here. Binding to object is temporarily invisible. See, in the C++ code, this reference my object points to this, whatever was created at this point and dereferenced. However, inside this block, it no longer points to it. Instead, it points to this, right? So within this block, there is a hole. The hole is that you cannot access this memory at all from within this block, at least not through this name. If you want to, you would have to choose some other name. And this is referred over here by this discontinuity as well. Okay. All right. Where did we go? So yeah, this is what it is. Non-local objects can be hidden. All right. So some languages, for example, Ada and C++, have qualifiers or scope resolution operators. In C++, it's the double colon. You can explicitly mention that you want to access a global scope thing. Yeah. So to some degree, it gives you visibility into the global, even if an object of the same name is being used somewhere deep in the nested function or function chains, because you could use the scope resolution operator to tell your intent that you, over here you do not want to use the local variable with the same name, but instead the global variable with the same name. All right. All right, blocks and local variable scope. So yes, in C, the scoping is controlled by this curly braces blocks. In C++ and Java, declarations may appear where statements may appear, and the scope extends to the end of the block. Again, the block is still the king. Scope is in C, C++, Java is related to the curly braces block. The local objects are stored in part of the subroutine frame reserved for temporaries. All right. Modules and object scope. Modules are the most important feature of a programming language that supports the construction of large applications. So this is what you call a library, right? Teams of programmers can work on a separate module files in a large project. Modules encapsulate variables, data types, and subroutines such that objects inside are visible to each other. Objects inside are not visible outside unless exported, that is with a clear intent. Objects outside are not visible inside unless imported with a clear, clean intent. You know, the idea is that you want, when you're in a team or even if you're coding yourself, you want to be crisply clear. What is it that you intend to do? so that the compiler does accordingly if it is allowed by the language, right? Ambiguity is a bad thing. That is the idea. No language support for modules in C and Pascal, not in the way this guy refers. C++ has the concept of namespaces. All right. Java class source files and libraries can be viewed as modules. Actually, this is not entirely true. There is support of modules in C as well. You can export variables. You can do your magic with header files and stuff. So this is not entirely true. That support might not be as formalized in language constructs as this guy wants to, or as it is available in other languages. But it's not like it's not there in C. All right. So we go to dynamic scope. Scope rule is that the current binding for a given name is the one encountered more recently during execution, right? So if every other thing is constant, what is the probability? The probability that the binding that you have most recently used in a code would be the one that is referred closer to it, right? So it's called the proximity, and this idea of a proximity based uh, um, optimization, so to say, is used amply inside computer science. This is the concept behind the layering of caches and many other things. Memory Manager heavily relies on this. All right, so typically adopted in early functional languages that are interpreted. Perl version 5 allows you to choose scope method for each variable separately with the dynamic scope. Name to object bindings cannot be determined by a compiler in general. Right? It's at odds the basic it's a conflicting requirement, right? So you cannot have the bindings be totally and absolutely dynamic, and you cannot have it supported by the compiler at compile time. It doesn't add up, right? Easy for the interpreter to look up name to object binding in a stack of declarations. Yeah, interpreter or language runtime during program execution can do a lot of those things and can enforce dynamic scoping rules, whatever they might be. All right, generally considered to be a bad programming language feature, I would agree. Hard to keep track of active bindings when reading a program text. Most languages are now compiled or a compiler interpreter mix. Well, this is an old article from 2003. So this dynamic scoping has had a resurgence. Many languages that are used today, JavaScript being the foremost, has a lot of dynamic typing and dynamic scoping. All right, sometimes useful. Unix environment variables have a dynamic scope. Okay, dynamic scope problem. In the following example program, function scaled score probably does not do what the programmer intended. See, ambiguity and is a killer. You need to be crisp clear with dynamic scoping. Max score in scale score is bound to foo's local variable max score after foo called scale score, which was a most recent binding during execution. Okay, let's see what is this guy doing. This is the function max score. All right, function scale score, raw score, integer. I don't understand this pseudo code, whatever this is using. I can't really comment. Let's move forward. I don't know this pseudocode syntax, so let's move forward. Also, compiler cannot always determine the type of a non-local variable in a subroutine, and runtime type checking is required. Yes, that is true. Compiler cannot do that. But then again, it's an intentional design choice when you do that you do when you choose to use or design a dynamically scoped language to whatever degree that scoping is allowed, right? The more you are loose about dynamic scoping, the less you can enforce it at compile time. That is the idea. Implementation of dynamic scope. Each time a subroutine is called, its local variables are pushed on a stack with their name to object binding. We know that. When a reference to a variable is made, the stack is searched top down for the variable's name to object binding, all right, to find the most recent one. After the subroutine returns, the bindings of the local variables are popped. It's a stack, right? Remember, so they're popped. Different implementations of a binding stack are used in programming languages with dynamic scope, each with advantages and disadvantages. All right. So, referencing environments. So, this is details. Let's ignore those. We are not designing languages here. We just want to understand the concept so that we are aware of it in whatever language we are choosing to deal with. All right, deep and shallow binding in dynamically scoped languages. The following program demonstrates the difference between deep and shallow binding. It's again about scoping basically, that which named version do you want access to. So we've covered this in a sense earlier already. I'm skipping those. Implementation of deep bindings, let's ignore. All right. Deep and shallow binding in statically scoped languages. Let's see this. Shallow binding has never been implemented in any statically scoped language. Deep binding in a statically scoped language is the obvious choice because in a statically scoped language, you want thing to be very crisply defined, right? Any variable, its usage, its type, you need to be crisp about it. They require more work by a compiler and at runtime, lesser so at runtime, but at compile time also. For example, in the program below, static scoping binds stress in older to the globally declared threads, so shallow binding does not make sense. So yeah, this is some example in pseudocode that I don't understand. And let's move forward. This is again details. Okay, first class subroutines, let's just ignore. So yeah, let's target overloading and bindings. So in an object-oriented language, function overloading is a very useful feature of the language, right? A name that can refer to more than one object is said to be overloaded. For example, the plus addition operator is used for integer and floating point addition in most programming languages, and in C++ it can be um, overloaded. Semantic rules of a programming language require that the context of an overloaded name should contain sufficient clues to deduce intended binding. This is the key. We don't want things to be ambiguous. The more the information, the better it is. And the language constructs of languages like C++ and Java, they do uh, provide detailed guidance on it. All right. Semantic analyzer of a compiler uses type checking to resolve bindings. Yeah. ADA, C++, and Java subroutine overloading enables programmer to define alternative implementations depending on argument types. Yes. All right. For example, in C++, there is this structure called complex. There's an enumeration, and these are the enum values. So there is a print number function which takes an integer. There's a print number, it takes integer and base. There is a print number function which takes a structure. So depending on which argument you would call it with, the runtime um, will pass it on to the relevant implementation, and the compiler is also aware of it because it's neatly and crisply defined. The intent is clear. All right. So ADA, C++, and Fortran 90 allow built-in operators to be overloaded with user-defined functions. Yeah. For example, even the basic arithmetic operators like plus, minus, and so on and so forth, you can override them and have your own classes, use addition as you like. All right. Polymorphic subroutines. So let's just ignore this, but clearly it has bearing on names as well. Polymorphism is basically, in a sense, the ability for a named object to take many forms, right? Even though, let's see, Lisp, ML, Haskell, and Smalltalk allow programmers, even Java and C++ obviously does that too. Um, so yeah, polymorphism is now pretty much a key pillar of object-oriented programming. All right. Thank you. I hope this was useful. This is a very good article, and I thought I'll try to make it easy for novices who are going through this by explaining it. Thank you. Have a good day. Bye.